Imagine we have a wave here, guys. This gray line here represents the undisturbed medium. The moment you disturb it here, you will be having a wave represented by the green wave here, the green curve. Okay, it goes this way and continues here. Okay, and as you can see, the wave direction is represented by the arrow. And based on our discussions in the previous lessons, we know that this wave carries itself the energy. Okay, this energy, and as it goes from here to there in that rightward direction, this energy is being transferred. Okay, this is happening in this type of wave called progressive wave. What we considered so far in our previous lessons are all progressive waves. Okay, it's happening like that. The wave is being transferred from here towards this direction. Okay, it's being transferred by the wave. All right, now after some time, this gray diagram here is going to be here. Alright, the one represented by the red curve around here. Alright, now if you're going to look at this point, which is, imagine this is a particle originally from the undisturbed medium. Okay, because of the wave, because we disturbed this part here and we have created a wave like this, represented by the green one, you can easily see that this particle should be moving somewhere here. Alright, this one here. Alright, this particle, this yellow one, should be around here already. Alright, now that is when this wave is this one. Alright, the green one. Now after a while, the wave will be moving somewhere here because it's propagating this way. Alright, represented by the red curve. Okay, meaning to say, this same particle here should be somewhere here already. Alright, and after some time, maybe there's another wave around here. Okay, this means that the particle is going to be somewhere here. Okay, somewhere here. Alright, okay, if you are actually by doing the disturbance here, disturbing the medium like that, alright, then you will be seeing these other parts in here. We can just extend lines around here. Okay, so basically, if you're going to look at it from the equilibrium position, the particle can just go up like that, up to this point, and then it can just go down, alright, back to here. It can also be moved somewhere here, alright, somewhere here. So basically, the movement of particle, actually any particle in this medium is like going up here. This is the maximum, and then it goes down there, around here, which is also the maximum, below the equilibrium position. Alright, now this part here, from the equilibrium position to the highest point, we already know that this one is amplitude. And just like what I told you a while ago, each particle is going to be having the same value for amplitude. Alright, if you choose a particle around here, it can also reach that high and it can also reach that low. Alright, okay, now imagine we copy the first wave or the first snapshot that we took a while ago, the green one. Alright, I just copied it around here. If you are going to put a barrier at the right side like here, something that can reflect the wave entirely, you will see that this one will bounce somewhere here. Alright, goes here and here. Okay, so it's gonna be this. Alright, like that. And if there's another barrier here, this, if it will be going back, but the path, or like the drawing, is going to be the same thing as this. Okay. Now, the energy here, therefore, is just contained within this area. Okay. We can therefore say that the energy is stored here. All right. In comparison with what is going on in the progressive waves. All right. In this kind of wave, which is obviously different, this is not progressive, the energy is being stored. Alright? And this kind of wave, something that looks like this or behave like this, is called stationary wave. Alright? Other resources call this standing wave because you will be seeing this only. You won't be seeing some patterns around here different from this one. Okay? This is the so-called stationary wave. And remember, this is the energy here is stored, in contrary to the progressive wave where the energy is being transferred by the wave itself. Alright, now imagine, just like what we did here a while ago, we have a particle here, and this particle can just be vibrating, moving up there, and then it goes down, and then can move up there also. Alright, however, it cannot go up here. Unlike in the progressive wave, they can reach the same peak. The particles are limited to some value of amplitude. Alright, like the amplitude here may be different from the amplitude here of this particle around here. Okay, this particle can go there, it can go down there also, and it can go up. Alright, if you're going to compare these two, this one can reach higher location as compared to this particle. Alright, now this part in this standing or stationary wave where the particles are actually not moving. This part here do not go up or down. Alright, this special position here is actually what we call node. Alright, node. We use the symbol N for that. Okay, now this one where the particles can actually be displaced at the highest location is actually a point called Antinode. Alright, the symbol that we are going to use here is capital A. Alright, however, look at this. We also use A here to represent amplitude a while ago, and maybe we can just erase this one, because this one is amplitude, the other one is a symbol for antinode. Maybe we just erase this one. Okay, and represents it with the italics, alright, or the italicized capital letter A. Anyway, in the Cambridge, the one that I see in most of their exam is that every time there is a variable, they represent it in italics. They italicize the letter like that. If it's not italicized, it would mean it is a name of a point or a name of the part of a certain diagram, like this one, antinode, and the node. These are just written normally, alright, meaning they are just name of some special points, alright, in our diagram. Now here we have an amplitude, italics, okay. This is a variable, alright. Now the amplitude in this standing wave or stationary wave, okay, this one is 0 at all the nodes. Okay, they don't move. The particles here don't move up or down. They remain in their equilibrium position. Okay, even there's a wave around. Okay, now the amplitude is maximum at this point here. All right, or any antinodes. This is one antinode. We have here an antinode also, and there's another antinode here. Alright, so those are the things that you have to remember when it comes to these special points here, the nodes and the antinodes. You can use the idea of having 0 amplitude for the nodes and maximum amplitude for the antinodes. Alright, okay. Alright, imagine we have 2 barriers here, and let's say we have a wave like that. You cannot do this every time you create a wave. Alright, there is some specific frequency that you can get a wave that looks like this. Okay, now say for example it came from here, and then after reaching this part here, there's a barrier, so you know that this one should be reflecting. Alright, like that. Okay, it should be reflecting like that. And this part here, just like what I explained in the previous slide, is that the N, alright, both the this part here, this point here is a node. This one is a node here also. We can just put the name there. Alright, we have here the node, a node, and of course we also have an antinode. Alright, let's see. We can draw another stationary wave with this kind of figure. Say, imagine we disturb this part. We say if there's a medium around there, maybe a rope, you can create a wave like this, and you have one complete cycle. Alright, up to here. Alright, then it will reflect such that we will be having a diagram similar to this one. Okay, The same thing, we can call this node, another node here, and also a node there, alright, and amplitude, no, sorry, this is antinode here and another antinode there, alright. Now we can also have something like this, right? We draw a wave like that, okay, and then the one reflected should be like that, okay. There are many nodes here, you see, okay, this one also, and you know that this one is an antinode, this one also antinode, and this one, okay. Now imagine that you know this length, alright, you know this length, alright, we call this length L, alright, we call this length L, alright. Another idea that you can get from this kind of stationary wave, if you were able to produce a stationary wave, now we can easily calculate from there the wavelength, or this one, the one represented by the symbol lambda. Alright, as you can see in this first diagram here, one complete wave, if there was no barrier here, it should be somewhere around here. Alright, that's one complete wave. So the wavelength should be this one, alright, up to here. Okay, if you know that this one is 1L, then the wavelength should be 2Ls. Alright, so we can put it like that. Alright, 2L. Alright, and just like what I was saying a while ago, this is not something that you can do easily. Alright, there must be a particular frequency that you can do this thing. Alright, you can try do some trial and error, something like that, when you are trying to produce a wave, and the wave that you want to produce is a stationary wave like this. Alright, there is a particular frequency that you can do this. Alright, a frequency other than that, you might not be able to create a wave that looks like this. Alright, and that frequency we can denote it with F subscript 0. Alright, this thing is called fundamental. Alright, you have to remember, if you have this kind of stationary wave, this is fundamental. Alright, we have the frequency around here. Alright, and the wavelength is twice the length, if you know this distance or this length. Alright, now how about this one? Okay, this one, you see the wavelength here is going to be different. As you can see, from this part going to this part, you have one complete vibration, and therefore this distance represents your wavelength, and that is equal to L. So in this kind of standing wave, with this kind of similar diagram like this, the wavelength is going to be equal to the length. Alright, the length here, alright, or this distance L. Alright, we have a special name for this. We call this second harmonic. Alright, this one is fundamental, or you may also call it first harmonic, and this one here is going to be called second harmonic. Alright, now based on the number of wave that you can produce per second, if you have this, which is called F sub 0 or F sub O, we can also say that relative to that, the frequency of this stationary wave here should be twice this frequency of the first one. Alright, that's why I wrote here 2F sub 0. Okay? Okay, so first harmonic, second harmonic, and you can guess that this one here should be called third harmonic. Alright, and it is. Okay, now the wavelength here is going to be this one. Alright, because as you can see, this one is L, and it looks like this drawing is dividing the L into 3, and 2 parts is going to represent the wavelength. Alright, so we can put here our wavelength in a third harmonic is 2/3 of L. Alright, and you can only do this if you increase the frequency again. Alright, you increase the frequency again. You see, you have one wave here. Alright, so there is more wave per second this time. Alright, if you're going to compare the frequency here in the third harmonic to the first harmonic, then it has to be this one, 3 times of the F sub 0 or F sub O. Okay, and there will be more other types of stationary wave around here. Okay, depending on the frequency, and then you can call them fourth harmonic, fifth harmonic, and so on. Okay. Now, just for a simple application of this, we try to I tried to copy a problem from your textbook. All right, this one. Well, I got this from your textbook. And as you can see here, we have frequencies given and also some distances, which is actually this one 20 centimeter. And there is a description here also, another important information for you. There are 3 antinodes between 2 nodes. All right. The question is asking for the wavelength, and the other one is asking for the wave speed. Okay. Maybe in order for this to be solved easily, you should have some picture in mind, what's going on around here. If you want, we can draw something here, and you can mark this as one of the nodes being mentioned. Alright, these 2 nodes being mentioned here. Alright, the 2 nodes. And this distance here is 20 centimeter, as explained in the problem. Alright, and according to the problem, there are 3 antinodes. Alright, you can just put antinodes around there, and it's not going to be very hard to see that there should be some nodes around here. Alright, in order for you to have different nodes here. Okay, if there are no nodes here, then it will look like, you know, there's no other antinode except for the one of the middle. Alright, so there has to be 2 additional nodes here apart from these 2 nodes that were given in the problem. Alright, now we can try to draw the graph here. Okay, it should be like that, and then if it reflects, if there's a barrier around there, then we can have this. Alright, so based on our other slide a while ago, it looks like this one is third harmonic. Alright, it's the third harmonic where the frequency as compared to the fundamental is 3 times, alright, of this f sub o. And this frequency in the third harmonic is given also, which is 2500 hertz or 2500 hertz. Okay, and you know that if it's a third harmonic, the wavelength can be calculated using this. Alright, 2/3 of the length. We know the length. Our length is 20 centimeter here. Okay, so it's gonna be very easy to calculate this wavelength here for the first question A. Okay, it's just 2/3 of 20 centimeters, which is going to be 13 centimeters expressed in the proper number of significant figures. Alright, now for letter B here, we need to calculate for the sound. Alright, the speed of the sound, and the formula is already given here. Okay, so V is equal to 0.13. The reason why I put 0.13 here is because I want the values to be expressed in the SI units. Alright, from centimeters, this has just been converted into meters. Alright, and then you are going to multiply that with the frequency. But you don't need to divide this 2500 here by 3. Okay, we need the frequency of the wave in question. Okay, this one, if you divide it by 3, then what you will be having is the frequency of another wave. Alright, the first harmonic. Alright, what we want is the speed of this sound wave showing third harmonic. Alright, and then so we multiply this by 2500, and therefore we have in the end 330 meter hertz or 330 meters per second. Okay, all right.